Southern Appalachians, autumn of 1750. While neighboring Cherokee families quickly erected standard bark and log winter lodges before the first snow, 47-year-old Atatsi Uli was still excavating in his third week, digging a chamber 4.5 feet into a hillside that would require 3 times the labor of conventional shelters. His fellow tribe members called it a hole in the dirt for winter. The tribal elders shook their heads, dismissing his underground dwelling as wasteful preparation when proven lodge designs had protected families for generations. Then the brutal Arctic blast of December 1750 arrived. Temperatures plunged to 10 below zero for 14 consecutive nights, with wind chills reaching 25 below. The harshest winter conditions in living memory that would test every shelter in the valley. Standard lodges saw interior temperatures drop to the 20s, forcing families to burn 4 times their usual firewood while suffering frostbite and exposure deaths. But Atatsi Uli's strange underground winter house maintained interior temperatures in the mid-60s with minimal fuel, sheltering his family in complete comfort while others fought for survival. What did this Cherokee builder understand about the Earth's thermal properties that conventional tribal wisdom had completely missed? The morning mist clung to the ridges of the southern Appalachians as Atatsi Uli stood on the slope he had been studying for weeks, his weathered hands testing the soil composition one final time. At 47, he possessed the measured patience of a hunter who had tracked deer through 15 winters, and the methodical mind of a builder who understood that survival depended on preparation, not luck. His wife Nicha watched from their temporary shelter as he drove a bent sapling probe deep into the hillside, counting the depth until it struck the layer of clay-rich earth he sought. The previous winter of 1749 had nearly claimed his family. Their conventional bark and log lodge, built according to the methods passed down through generations, had proved inadequate against the bitter cold that descended in January. Interior temperatures had dropped to 28 degrees on multiple nights, forcing them to burn through their firewood reserves at an alarming rate while his children shivered beneath layers of deer hide. His father, Tsali, weakened by the cold, had died that February, and Atatsi Uli had vowed then that he would never again trust his family's survival to methods that had failed when truly tested. Throughout the summer of 1750, he had observed the land with new eyes. On hunting expeditions to the higher elevations, he noticed how certain natural caves maintained steady temperatures even during the hottest days. He studied the way water behaved in shallow versus deep springs, noting that springs emerging from greater depths ran cooler in summer and warmer in winter. Most importantly, he had spent time with visiting Cherokee from the Chickamauga settlements, learning about their experiments with earth-bermed shelters that used the ground itself as insulation. When he announced his intention to dig a winter house into the hillside, the response was immediate and predictable. Elder Guy Uya, whose 68 years carried the authority of successful leadership through countless seasons, declared the plan foolish. The respected elder had guided his clan through 7 previous winters using lodges that could be erected in 5 days, consuming minimal labor and materials. Why, he demanded, would any sensible man waste 3 weeks digging into dirt when proven methods served adequately? Young Nawati, at 34, the rising voice of his generation, was even more direct in his criticism. He measured worth in hunting days and lodge efficiency, pointing out that a conventional shelter required only 6 days of construction and provided adequate protection for the investment of time. Atatsi Uli's proposed excavation would consume 21 days of labor that could be spent hunting, gathering winter provisions, or preparing other essential survival resources. The technical challenges of Atatsi Uli's design were indeed formidable. He planned to excavate 4.5 feet below the natural ground level, creating a circular chamber 12 feet in diameter with walls rising 7 feet above the excavated floor. The roof would require 40 carefully selected saplings, bent and positioned as ribs spaced at 18-inch intervals to support multiple layers of covering materials. The entrance would be an 8-foot tunnel, 3 feet wide and 5 feet high, sloping downward 6 inches below the main floor level to create what he called a cold air trap. Most ambitious of all was his planned roof system. Over the bent sapling framework, he intended to layer bark strips 1.5 inches thick, followed by 8 inches of clay grass mixture, requiring 1,200 pounds of clay and 300 pounds of river sand. The final layer would be 10 inches of carefully dried thatch, creating a roof system nearly 2 feet thick at its densest points. The interior finishing would demand equal precision. He planned to apply plaster made from clay, sand, and crushed mussel shells across 50 square feet of wall surface, the shells providing fine porosity to manage moisture while reflecting heat from the central hearth. Sleeping platforms would be constructed 2 feet above the main floor, each sized at 6 feet by 4 feet, and layered with spruce bark mats and 4 inches of dried deer hide padding. As autumn progressed and conventional lodges rose quickly around the settlement, Atatsi continued his methodical excavation. His children, 15-year-old Kai, 12-year-old Seli, and 9-year-old Lona, helped haul clay and sand, learning the construction methods through direct participation. Nicha prepared the mussel shells, crushing them to the proper consistency for interior plaster, while managing the family's daily needs from their temporary shelter. The mockery intensified as neighboring families completed their winter preparations in the traditional time frame. Clan leader Agusila, responsible for ensuring his community's readiness for winter, publicly questioned why they should trust experimental methods when established techniques had protected their ancestors. The phrase dirt hole became common shorthand for describing Atatsi Uli's project, usually accompanied by predictions that the excavated chamber would flood, collapse, or prove impossible to heat effectively. By late October, when the first snow began dusting the higher ridges, Atatsi Uli's underground winter house was finally complete. The entrance tunnel descended at the planned angle, the layered roof rose in a gentle dome above ground level, and the interior hearth sat ready for its first fire. His neighbors had finished their conventional lodges weeks earlier and were already settling into their winter routines, confident that their proven methods would see them through another season. None suspected that the approaching winter of 1750 would test every shelter in the valley beyond anything in living memory, or that the man they called foolish for, digging into the hillside, had prepared for conditions that would soon arrive with devastating force. The Arctic blast arrived on December 2nd, 1750, with a ferocity that caught even the most experienced weather observers off guard. What began as typical early winter cold quickly intensified into conditions that would persist for 14 consecutive nights, with temperatures plunging to 10 degrees below zero and wind chills reaching 25 below. The sustained cold represented the harshest winter conditions in the collective memory of the valley town's Cherokee, testing every structure and survival strategy in the settlements. In Elder Guy Uya's lodge, the crisis manifested immediately. The conventional bark walls, approximately 4 inches thick, provided insufficient insulation against the relentless cold penetration. Interior temperatures dropped precipitously to between 20 and 25 degrees on the first night, forcing the family to maintain fires that consumed 4 times their normal fuel allocation. The single-layer thatch roof, adequate for typical winters, allowed heat to escape rapidly while permitting cold air infiltration around the edges, where bark sections had contracted in the extreme conditions. The fuel crisis escalated quickly across the settlement. Families that had prepared standard winter firewood supplies found themselves burning through reserves at an unprecedented rate. Where 1 cord of wood typically lasted a month during normal winter conditions, lodges now consumed that amount in a single week. Hunting parties that should have been tracking game instead spent daylight hours desperately gathering additional fuel, competing for increasingly scarce dead wood in the surrounding forest. Meanwhile, Atatsi Uli's underground winter house demonstrated the effectiveness of his unconventional design principles. After loading his hearth with a single charge of seasoned oak, weighing approximately 44 pounds on December 2nd, he banked the coals and allowed the fire to smolder at minimal intensity. The thermal mass of the surrounding earth, combined with the layered roof insulation, retained and slowly released heat throughout the structure. Interior temperatures stabilized between 65 and 70 degrees, maintained by the stored thermal energy rather than continuous active heating. The entrance tunnel functioned exactly as Atatsi Uli had calculated. Cold air, being denser than warm air, flowed down the sloped passage and settled in the lower section, creating a natural barrier that prevented frigid exterior air from reaching the main living chamber. The 6-inch drop below floor level effectively trapped this cold air mass, while the warm air generated by the minimal hearth fire rose naturally and circulated within the living space above. As the extreme cold persisted into its second week, structural failures began occurring in conventional lodges throughout the valley. Heavy wet snow accumulated to depths of 2 feet, creating loads of approximately 20 pounds per square foot that exceeded the design capacity of single-layer thatch roofs. Elder Guy Uya's lodge developed significant sagging, allowing water infiltration that froze overnight and created dangerous ice accumulations inside the structure. Similar failures occurred across the settlement as roofs designed for normal snow loads buckled under the unprecedented weight. Young Nawadi's lodge suffered a complete heating system failure on the 5th night of sub-zero temperatures. The combination of inadequate ventilation and extreme cold created conditions where his hearth fire consumed available oxygen faster than the structure could provide fresh air circulation. When the fire died due to oxygen starvation, interior temperatures plummeted to between 15 and 20 degrees within hours. Desperate attempts to restart the fire in oxygen-depleted conditions proved futile until morning, when ventilation could be restored, but the damage was done. One of his hunting companions developed severe frostbite that would later require amputation. The human cost mounted steadily as the crisis extended beyond anyone's expectations. Of the 18 adults in the immediate settlement area, 6 suffered varying degrees of frostbite injuries. 2 elderly residents died from exposure-related complications during the 3rd week of extreme conditions. These casualties occurred despite heroic efforts to share fuel resources and provide mutual assistance among families whose individual heating systems had failed. Atatsi Uli's fuel consumption during this period remained remarkably low. His weekly wood usage averaged approximately 1/4 cord, representing an 80% reduction compared to the consumption rates of conventional lodges. This efficiency resulted directly from the earth shelter's superior insulation properties and the heat retention capabilities of the clay grass roof layering system. Where other families exhausted their fuel reserves and faced impossible choices between warmth and food preparation, Atatsi Uli's household maintained comfortable living conditions without depleting their winter provisions. The social dynamics within the settlement shifted dramatically as the crisis intensified. Families whose lodges had failed began seeking shelter with relatives or neighbors whose structures remained functional. However, even successful conventional lodges struggled to accommodate additional occupants without overwhelming their already stressed heating systems. The mathematics of survival became brutally clear. Each additional person required proportionally more fuel and space in structures already operating at maximum capacity. When clan leader Agusila's lodge collapsed under snow load during the 2nd week of January, he faced the humbling necessity of requesting shelter from the man he had publicly criticized. His arrival at Atatsi Uli's entrance tunnel, accompanied by his immediate family, represented a dramatic reversal of the social dynamics that had dominated the autumn construction period. The underground winter house that had been dismissed as foolish excavation now stood as the most reliable shelter in the settlement. The final test came during the last week of January, when a second wave of Arctic air combined with sustained winds exceeding 45 miles per hour. Wind chill factors dropped to 40 degrees below zero, creating conditions that rendered even brief outdoor exposure potentially fatal. Several remaining conventional lodges that had survived the initial cold wave finally succumbed to the combination of structural stress and heating system failure, leaving their occupants with no choice but to seek emergency shelter wherever it could be found. The interior plaster system revealed its sophisticated engineering as the extreme conditions persisted into January. Atatsi Uli's careful mixture of 60% clay, 30% river sand, and 10% crushed mussel shell created a surface that actively managed moisture while maximizing heat reflection. The mussel shell fragments, ground to powder consistency, provided microscopic porosity that absorbed excess humidity from cooking and breathing, preventing the condensation buildup that plagued conventional lodges. Simultaneously, the shell's calcium carbonate composition reflected radiant heat from the central hearth back into the living space, creating an internal warming system that operated without additional fuel consumption. The elevated sleeping platforms demonstrated another critical design innovation. Positioned 2 feet above the main floor level, these benches placed family members in the optimal thermal zone where warm air naturally accumulated. Each platform measured 6 feet by 4 feet, sized precisely to accommodate individual family members while maximizing efficient use of the limited interior space. The spruce bark mats and 4-inch layer of dried deer hide provided insulation between the sleepers and the platform structure, maintaining surface temperatures near 60 degrees even when the floor dropped to 45 degrees during periods when the hearth was completely banked. Food storage within the underground chamber proved equally successful. The 120 pounds of winter squash and pumpkins stored beneath the bench seats occupied the coolest zone of the interior, where temperatures remained steady near 50 degrees. This thermal stability prevented the freeze-thaw cycles that destroyed provisions in conventional root cellars, where exterior temperature fluctuations caused repeated expansion and contraction damage. The metabolic heat generated by the slowly respiring vegetables actually contributed to the overall thermal balance of the shelter, creating a symbiotic relationship between food preservation and space heating. Ventilation management became critical as additional families sought refuge in the underground structure. The roof vent funnel, approximately 6 inches in diameter at the apex, created a natural chimney effect that drew stale air upward, while the entrance tunnel gap allowed fresh air infiltration. When exterior winds exceeded 15 miles per hour, the pressure differential intensified this circulation pattern, pulling oxygen-rich air through the tunnel while expelling combustion gases through the roof opening. This passive system prevented the carbon monoxide buildup that had claimed lives in poorly ventilated conventional lodges, where desperate families had sealed every opening to retain heat. The structural integrity of the layered roof system proved its worth under sustained snow loads. The bent sapling ribs, positioned at 18-inch centers, distributed weight effectively across the dome structure. The progressive layering, bark, claygrass mixture, and thatch created a composite material stronger than any single component. As snow accumulated on the surface, the outer thatch layer compressed slightly, creating an additional insulation barrier while the inner claygrass layer maintained its structural integrity. Water from melting snow percolated through the thatch and froze in the clay layer, creating an impermeable ice barrier that sealed the structure against further infiltration. When clan leader Agusila arrived with his family following his lodge collapse, the underground winter house faced its ultimate capacity test. 10 people now occupied a space designed for 5, yet the thermal dynamics remained stable. The additional body heat from extra occupants offset the increased oxygen consumption, while careful scheduling of cooking and sleeping arrangements prevented overcrowding problems. Atatsi Uli implemented a rotation system where some occupants slept during daylight hours while others remained active, maximizing efficient use of platform space and maintaining air quality through natural circulation patterns. Fire management became more critical with increased occupancy. Rather than maintaining continuous flames, Atatsi Uli perfected a banking technique using oak coals covered with fine ash that sustained combustion for up to 16 hours without active tending. This method provided steady heat output while minimizing smoke production and oxygen consumption. The thermal mass of the clay walls stored heat during active burning periods and released it gradually, maintaining comfortable temperatures even when the fire appeared nearly extinguished. The psychological impact of the shelter's success extended beyond mere physical survival. Families who had spent weeks shivering in failed conventional lodges experienced profound relief upon entering the stable 65-degree environment. Children who had developed respiratory problems from constant cold exposure recovered quickly in the warm, humid conditions. Adults who had exhausted themselves gathering fuel and maintaining failing heating systems could finally rest and focus on other survival priorities like food preparation and equipment maintenance. Resource sharing among the shelter's occupants created an informal community that operated more efficiently than individual family units, struggling in separate failing structures. Women coordinated cooking schedules to maximize fuel efficiency from the single hearth. Men organized hunting expeditions that provided fresh protein while reducing pressure on stored provisions. Children assisted with maintenance tasks like ash removal and ventilation monitoring, learning the underground shelter's operational principles through direct participation. As word of the shelter's success spread beyond the immediate settlement, visitors arrived from neighboring villages to observe the structure and understand its design principles. These observers documented the interior temperatures, measured fuel consumption rates, and examined construction details with growing amazement. The underground winter house that had been dismissed as foolish excavation now attracted serious attention from Cherokee builders throughout the Valley Towns region who recognized its potential for improving winter survival rates. By the end of January, when the second wave of extreme cold struck with wind chills reaching 40 degrees below zero, conventional lodges throughout the area had largely failed. The underground shelter continued operating at optimal efficiency, providing refuge for displaced families while demonstrating the validity of Atatsi Uli's innovative approach to winter housing design. When spring thaw arrived on March 10, 1751, the extent of structural damage to conventional lodges became starkly apparent. Elder Guy Uya's dwelling showed severe deterioration where repeated freeze-thaw cycles had opened gaps in the bark walls, allowing water infiltration that rotted the interior support posts. The floor had subsided 3 to 4 inches in multiple locations where freeze expansion had fractured the underlying clay base, creating uneven surfaces that would require complete reconstruction. Similar damage patterns appeared throughout the settlement as families emerged from winter to assess structures that had failed progressively under unprecedented conditions. In contrast, Atatsi Uli's underground winter house showed no significant deterioration. The earth-bermed walls had remained stable throughout the thermal cycling, the layered roof maintained its structural integrity, and the interior plaster showed only minor surface cracking that required minimal repair. The entrance tunnel remained clear and functional, its slope design having prevented ice accumulation that blocked access to other shelters during the worst of the winter storms. Young Nawadi undertook the first documented replication of the underground design In late summer of 1751, having witnessed firsthand the thermal efficiency and structural resilience of Atatsi Uli's shelter, he selected a southeast-facing slope near his family's summer dwelling and began excavation. His version incorporated modifications based on his observations during the winter crisis. The chamber diameter measured 10 feet rather than 12, reflecting his smaller family size. While the tunnel length extended to 10 feet, with a 6-inch drop below floor level to enhance cold air trapping effectiveness. Nawati's construction timeline revealed the learning curve involved in replicating the technique. Where Atatsi Uli had required 3 weeks to complete his original excavation and finishing work, Nawati's project extended to 5 weeks as he refined his understanding of clay mixture ratios and roof layering sequences. His bent sapling ribs were spaced at 16-inch centers, slightly closer than the original design, while his clay-grass mixture incorporated local materials that required experimentation to achieve proper consistency and adhesion. Colonial trader John McCoy arrived in the valley towns during autumn of 1751 and documented the underground shelter phenomenon in his trading post records. McCoy, experienced in frontier construction methods, recognized immediately that the Cherokee earth shelter design exceeded the thermal efficiency of conventional log cabin construction used by European settlers in similar climates. His detailed measurements recorded interior temperatures of 62 to 68 degrees when exterior conditions dropped to 5 degrees below zero, representing thermal performance that contemporary colonial heating systems could not match. McCoy's observations extended beyond technical specifications to economic implications. He calculated that Cherokee families using underground winter houses consumed approximately 1/4 the firewood required by European settlers maintaining log cabins at equivalent interior temperatures. This fuel efficiency translated directly into reduced labor requirements for wood gathering and increased time availability for hunting, craft production, and other survival activities during critical winter months. Word of the underground shelter success spread rapidly through Cherokee trading networks during 1752. Visitors from the middle towns and out towns arrived specifically to examine construction techniques and interview families who had survived the devastating winter. These delegations brought their own innovations and modifications, creating regional variations that adapted the basic design to different soil conditions and climate patterns found throughout Cherokee territory. The replication process accelerated during the summer of 1752 when Elder Guy Uya formally endorsed the underground method and supervised construction of a communal version for emergency use. This larger structure, with a diameter of 18 feet, incorporated multiple hearth locations and enhanced ventilation systems designed to accommodate up to 20 people during crisis periods. The elders' endorsement carried significant cultural weight, transforming the underground shelter from experimental innovation to accepted community infrastructure. Archaeological evidence from this period, discovered at sites throughout the southern Appalachians, confirms widespread adoption of semi-subterranean winter structures. Excavations have revealed circular foundations with diameters ranging from 10 to 25 feet, central hearth features, and post hole patterns consistent with domed roof construction. These archaeological remains validate historical accounts of the technology's rapid dissemination through Cherokee communities. European colonial settlers, initially skeptical of Native American building methods, began secretly adopting underground shelter techniques after experiencing catastrophic heating failures during subsequent harsh winters. Colonial records from 1753 and 1754 document several instances where frontier families constructed earth-bermed shelters adjacent to their main dwellings, using them as emergency refuges during extreme weather events. These structures, though crude compared to Cherokee originals, provided the thermal efficiency necessary for survival when conventional log cabin heating proved inadequate. The social transformation within Atatsi Uli's own community reflected broader changes in attitude toward innovation and traditional practice. By 1753, his construction methodology had been codified into teaching protocols that ensured proper technique transmission to younger builders. His son Kay, now 18, had mastered the excavation and layering procedures sufficiently to lead construction projects for other families, while his daughters had become expert in interior finishing techniques and thermal management principles. Clan leader Agusila implemented formal winter shelter requirements for his jurisdiction, mandating that all new winter dwellings incorporate either tunnel entrance design or enhanced insulation systems based on underground shelter principles. This policy represented institutional recognition that conventional methods, while historically adequate, required modification to address changing climatic conditions and ensure community survival during extreme weather events. By 1755, the underground winter house had evolved from radical experiment to established technology, with Atatsi Uli serving as consultant for construction projects throughout the Valley Towns region. His quiet vindication was complete. The man who had been mocked for digging holes in hillsides had fundamentally transformed Cherokee winter survival strategy through careful observation of natural principles and methodical engineering application. Archaeological excavations conducted in the 1940s through 1970s at Cherokee sites throughout the Blue Ridge Mountains uncovered compelling physical evidence of the underground winter house tradition. At the Mealiquos site in eastern Tennessee, archaeologists discovered circular depressions with diameters ranging from 20 to 25 feet, surrounded by post hole patterns indicating sophisticated dome construction. Soil analysis revealed layers of clay, organic matter, and fire-cracked rock consistent with the thermal mass systems described in historical accounts. Carbon dating placed these structures between 1700 and 1800, confirming their use during the period when Atatsi Uli's innovations were spreading throughout Cherokee territory. The rediscovery of earth-sheltered building principles by modern engineers occurred independently during the post-World War II housing boom. Energy-conscious architects in the 1950s began experimenting with earth-bermed homes, driven by rising fuel costs and growing awareness of thermal efficiency. Their calculations demonstrated that maintaining soil contact on three sides of a structure could reduce heating requirements by 60 to 70% compared to conventional above-ground construction. The ground temperature stability that Atatsi Uli had observed and utilized, 50 to 55 degrees at depths of 4 to 6 feet, became the foundation for passive solar design principles that dominated sustainable architecture through the remainder of the 20th century. Malcolm Wells, a pioneering architect in the earth-sheltered movement, published detailed studies in the 1970s documenting the thermal performance of underground structures. His measurements showed that properly designed earth-bermed homes maintained interior temperatures within 10 degrees of desired comfort levels using minimal supplemental heating, even during severe winter conditions. Wells's work validated scientifically what Cherokee builders had understood intuitively centuries earlier, that the earth itself provided the most reliable thermal mass and insulation system available to residential builders. Contemporary sustainable building codes adopted many principles first demonstrated in Cherokee winter houses. Modern earth-sheltered construction requires vapor barriers, drainage systems, and insulation materials unknown to 18th century builders, yet the fundamental concept remains unchanged. South-facing orientation maximizes solar gain, earth berming provides thermal stability, and careful attention to ventilation prevents moisture problems that can compromise structural integrity. The sophisticated understanding of thermal dynamics, evident in Atatsi Uli's design, continues to inform 21st century green building practices. The Cherokee concept of ASII, or winter house, represented far more than emergency shelter. It embodied a comprehensive understanding of seasonal adaptation and resource management. These structures were not primitive accommodations, but sophisticated responses to climatic challenges that required precise observation of environmental conditions and masterful manipulation of available materials. The integration of food storage, thermal management, and social space within a single underground chamber demonstrated engineering principles that modern designers struggle to replicate, even with advanced materials and mechanical systems. Property owners seeking energy independence and emergency preparedness have increasingly turned to earth-sheltered construction as fuel costs rise and climate patterns become less predictable. Modern implementations typically involve excavation depths of 6 to 8 feet, reinforced concrete construction, and mechanical ventilation systems. Yet the core principles remain those demonstrated by Atatsi Uli's original design. South-facing orientation, thermal mass utilization, and passive air circulation continue to provide the foundation for efficient underground living spaces. The cultural wisdom embedded in Cherokee winter house construction extends beyond mere technical specifications to encompass broader principles of environmental observation and adaptive innovation. Atatsi Uli's willingness to challenge conventional methods while respecting natural systems exemplifies the balance between tradition and progress that characterizes successful long-term survival strategies. His careful documentation of ground temperatures, systematic testing of material combinations, and methodical refinement of construction techniques reflect the scientific approach that underlies all effective indigenous technology. Educational institutions throughout the southeastern United States now incorporate Cherokee winter house construction into their curricula as examples of sustainable design and cultural innovation. Students studying environmental science, architecture, and anthropology examine the technical specifications and cultural context of these structures to understand how indigenous communities developed sophisticated solutions to environmental challenges using locally available resources and empirical observation. The Eastern Band of Cherokee Indians maintains a full-scale reconstruction of a traditional winter house at their cultural center in North Carolina. This structure, built using authentic materials and construction techniques, demonstrates the thermal efficiency and structural integrity that made underground shelters viable for generations of Cherokee families. Visitors can experience the interior environment and observe the passive systems that maintained comfortable living conditions without mechanical heating or ventilation equipment. Modern engineering analysis of Cherokee winter house design reveals principles that anticipate contemporary green building standards by 2.5 centuries. The integration of thermal mass, passive solar orientation, natural ventilation, and moisture management systems demonstrates a level of environmental understanding that rivals current sustainable design practices. When contemporary architects and engineers study these historical structures, they consistently acknowledge the sophistication of the engineering principles and the effectiveness of the implemented solutions. The fundamental lesson embedded in Atatsi Uli's innovation transcends specific construction techniques to address broader questions of survival philosophy and environmental adaptation. His success resulted not from rejection of traditional knowledge, but from careful observation of natural systems and willingness to modify established practices when conditions demanded innovation. The underground winter house that saved his family during the crisis of 1750 became a lasting contribution to Cherokee building tradition and a demonstration that preparation guided by empirical observation and respect for natural principles provides the most reliable foundation for surviving environmental extremes.